Hello there, and welcome to this gentle journey through time and space. I'm so glad you found your way here tonight. Perhaps you've had one of those days where your mind feels cluttered with earthly concerns, or maybe you're simply someone who finds peace in cosmic stories rather than counting sheep. Either way, you're exactly where you need to be. Tonight, we're going to travel back in time. Not just years or centuries, but 4.6 billion years into the past to witness the birth of our solar system. We'll watch as a simple cloud of gas and dust slowly transforms into the complex family of worlds we call home. You have nothing to do but listen and let your mind drift among the planets and moons, the asteroids and comets, all of which began as whispers of matter in the cold depths of space. Let your breathing slow and your thoughts settle. Feel the weight of gravity holding you gently in place, the same force that shaped everything we'll explore tonight. Because this isn't just a story about distant worlds. It's the story of how you came to be here, on this particular planet, in this particular solar system, made from materials that were forged in the hearts of ancient stars and gathered together in one of the universe's most beautiful acts of construction. Some of what you hear tonight might surprise you, and some might simply carry you toward peaceful sleep. Both are exactly right. This is a story told in deep time, where millions of years pass like seasons, and the patient work of gravity and physics creates wonders beyond imagination. Now, let's begin our journey to the very beginning, when our solar system was nothing more than a dream hidden in a cloud of cosmic dust. Far out in the depths of space, in what we now call the Orion Arm of the Milky Way galaxy, there drifted a vast cloud of gas and dust. This wasn't an ordinary cloud, the kind you might see drifting across an earthly sky. This was a molecular cloud, hundreds of times larger than our entire solar system, yet so thin that the finest vacuum chambers on Earth are denser by comparison. The cloud was ancient, even by cosmic standards, having drifted through space for millions of years. It was composed mostly of hydrogen, the simplest and most abundant element in the universe, along with helium and tiny grains of dust, no bigger than the particles in cigarette smoke. But this cloud was special. Unlike the very first generation of such clouds that formed after the Big Bang, this one had been enriched. Somewhere nearby, perhaps not long before in cosmic terms, a massive star had reached the end of its life and exploded in a supernova, scattering heavy elements across the region. The temperature within this cloud was almost beyond imagination, hovering around negative 440 degrees Fahrenheit. In this bitter cold, atoms moved sluggishly, and strange chemistry took place that would be impossible under earthly conditions. Water molecules froze onto dust grains, creating tiny ice particles. Carbon bonded with other elements to form complex organic compounds. Even in this seeming emptiness, the building blocks of life were already beginning to take shape. The cloud wasn't uniform. Like weather patterns in the Earth's atmosphere, it had regions that were slightly denser and others that were more diffuse. These variations were subtle, perhaps just a few more atoms per cubic inch in some places than in others. But in the patient arithmetic of cosmic time, these tiny differences would prove enormously important. Our future solar system was contained within just a small portion of this larger cloud, a region perhaps twice the mass of our current sun. The cloud rotated, but so slowly that it would take millions of years to complete a single turn. This gentle rotation was a legacy of the galaxy's own motion, a whisper of angular momentum that had been preserved from the cloud's formation. For perhaps 10 million years, this cloud drifted peacefully through space, slowly mixing its contents as weak magnetic fields stirred its interior. The dust grains occasionally collided with each other, sometimes sticking together to form slightly larger particles, sometimes bouncing apart. Ice accumulated on the grains in the coldest regions, while closer to distant stars, the ice sublimated back into gas. The cloud was a reservoir of potential energy. All that mass spread across such a vast region represented a delicate balance between the force of gravity trying to pull everything together and the random motion of atoms pushing everything apart. For millions of years, this balance held. The cloud was stable, content to drift and evolve slowly in the peaceful depths of space. But stability in the universe is often temporary. Somewhere in the cosmic neighborhood, events were unfolding that would soon disturb this ancient tranquility. The trigger came from violence born of beauty. A massive star, many times larger than our sun, had been burning brilliantly for perhaps 10 million years somewhere within a few hundred light years of our quiet cloud. These stellar giants live fast and die young, burning their nuclear fuel at prodigious rates that make them among the brightest objects in the galaxy. When such a star exhausts its fuel, the ending is spectacular. In a matter of seconds, the star's core collapses, then rebounds in an explosion so powerful it briefly outshines entire galaxies. The shock wave from this supernova raced outward at thousands of kilometers per second, carrying with it the heavy elements forged in the star's nuclear furnace. When this shock wave reached our molecular cloud, it was like a gentle hand disturbing the surface of a still pond. The wave compressed part of the cloud, increasing the density in certain regions and triggering instabilities that had been waiting millions of years to unfold. In the compressed regions, gravity finally gained the upper hand. Where before the cloud had been held in balance, now the inward pull of gravity began to overcome the outward pressure of the gas. What had been stable became unstable. What had been uniform began to fragment. The collapse didn't happen all at once. Instead, the cloud broke apart into smaller pieces, each destined to become a star system of its own. Our piece, the portion that would become our solar system, began its own private collapse toward a destiny that would include rocky planets, gas giants, moons, and eventually life itself. As the cloud contracted, something remarkable began to happen. The same principle that makes figure skaters spin faster when they pull their arms close to their bodies began to affect our collapsing cloud. As it shrank, it spun faster. What had been an almost imperceptible rotation became more and more pronounced. The collapse wasn't spherical. Instead, the cloud began to flatten, forming what astronomers call a protoplanetary disk. Material fell inward along curved paths, spiraling down toward the center like water draining from a bathtub, but on a scale that dwarfs human comprehension. Over the course of about 100,000 years, the cloud transformed from a roughly spherical mass of gas and dust into a flattened disk with a dense, hot center and cooler outer regions. The center would become our sun. The disk would become everything else: planets, moons, asteroids, comets, and all the small debris that fills the space between worlds. During this transformation, the temperature structure of the forming solar system was established. Near the center, where material was falling in rapidly and compressing under its own weight, temperatures rose to thousands of degrees. Here, only the most refractory materials could remain solid: metals and silicate minerals that would eventually form the cores of rocky planets. Further out, where the temperatures were cooler, different materials could condense. Beyond a certain distance from the center, which astronomers call the frost line, water could freeze into ice. This invisible boundary, located roughly where the asteroid belt is today, would fundamentally determine the composition of everything that formed in the solar system. The disk wasn't smooth or uniform. Turbulence, created by the collapse process, generated spiral patterns and density waves that propagated outward through the rotating material. These disturbances helped mix the contents of the disk and would later play crucial roles in planet formation. As the disk evolved, it also began to clear. The violent process of collapse heated the inner regions to such high temperatures that volatile materials, the light elements, and compounds that vaporize easily were driven outward. This left the inner regions enriched in refractory materials, while the outer regions became repositories for ices and gases. The disk was also threaded by magnetic fields, invisible lines of force that affected how electrically charged particles moved through the system. These fields created friction that caused material to spiral inward more rapidly than gravity alone would have managed. They also launched some material outward in the form of jets and winds, removing angular momentum from the system and allowing the central concentration to continue growing. For about 1 million years, this protoplanetary disk evolved and settled into a more stable configuration. The central object grew denser and hotter as more material fell onto it. The disk extended outward for perhaps 200 astronomical units, roughly 5 times farther than Pluto's current orbit. But the most dramatic changes were yet to come. Deep in the center of the disk, pressures and temperatures were approaching the critical thresholds needed for nuclear fusion. Our sun was about to be born. The moment of stellar birth is one of the most profound transitions in the universe. For nearly 1 million years, the central condensation in our protoplanetary disk had been growing hotter and denser as material continued to fall onto it. The temperature at the core had risen to several million degrees, and the pressure had become almost incomprehensible. At 15 million degrees Celsius, something magical happened. Hydrogen nuclei, which normally repel each other due to their positive electric charges, were moving so fast and being pressed so closely together that the strong nuclear force could overcome electromagnetic repulsion. For the first time, hydrogen began fusing into helium, releasing tremendous amounts of energy in the process. Our sun had ignited. This wasn't a gentle transition. The young sun was a wild, energetic object, quite unlike the stable star we know today. Astronomers call this phase the T Tauri stage, named after the first star of this type that was studied in detail. T Tauri stars are like cosmic teenagers, energetic and unpredictable, still settling into their adult personalities. The young sun was about 30% dimmer than it is today, but paradoxically much more active. It varied in brightness dramatically over periods of days or weeks, sometimes becoming 10 times brighter before fading again. Enormous flares erupted from its surface, releasing more energy than the most powerful solar flares of today. The solar wind, the stream of charged particles flowing away from the sun, was perhaps 1,000 times stronger than it is now. This intense activity had profound effects on the surrounding protoplanetary disk. The powerful solar wind began to clear gas from the inner regions of the solar system, blowing it outward and eventually beyond the sun's gravitational reach. Only the densest concentrations of material could resist this celestial gale. The young sun also launched bipolar jets from its north and south poles, streams of high-energy particles that extended for light years into space. These jets were like cosmic blowtorches, heating and ionizing the surrounding material and creating beautiful, glowing structures that we can still observe around young stars today. The X-ray emission from the young sun was thousands of times stronger than today's solar output. This high-energy radiation had the power to break apart molecules and strip electrons from atoms throughout the inner solar system. It was during this phase that many of the complex organic molecules that had formed in the original molecular cloud were destroyed, their atoms scattered to be incorporated into simpler, more stable compounds. But the T Tauri phase was also a time of creation. The intense energy output helped drive chemical reactions that wouldn't have been possible in the cold, dark molecular cloud. Simple minerals began to condense from the hot gas near the sun, forming tiny crystals that would eventually become the building blocks of planets. The sun's magnetic field during this time was incredibly complex and dynamic. Magnetic field lines extended far out into the protoplanetary disk, connecting the star to its surrounding material and affecting how matter moved through the system. These magnetic effects helped regulate the rate at which material fell onto the growing sun and played crucial roles in launching the jets and driving the powerful stellar wind. Over the course of about 10 million years, our sun gradually settled down. As it consumed its initial envelope of loosely bound material and found a stable balance between the inward pull of gravity and the outward pressure generated by nuclear fusion, it began to resemble the star we know today. The violent variability decreased, the flares became less frequent and powerful, and the solar wind weakened to more modest levels. By this time, the protoplanetary disk had been fundamentally transformed. The inner regions had been largely cleared of gas, leaving behind a thin distribution of solid particles, silicate dust, metal grains, and tiny crystalline fragments. The outer regions still retained significant amounts of gas, but even here, the disk was much less massive than it had been initially. The stage was now set for the next phase of solar system formation. With the sun shining steadily and the disk partially cleared, solid particles could begin the slow process of sticking together to form larger and larger objects. The era of planetesimals was about to begin. In the transformed disk surrounding the young sun, countless tiny particles drifted in lonely orbits. These weren't the original dust grains from the molecular cloud. Most of those had been destroyed by the sun's energetic youth. Instead, these were new particles, condensed from the hot gas in the disk's inner regions, or surviving as ice-coated grains in the cooler outer reaches. The particles were incredibly small by everyday standards. Most were no larger than the width of a human hair, and many were microscopic. Yet these tiny specks contained all the raw materials that would eventually become planets. Silicate minerals and metallic iron dominated the inner regions, while water ice, carbon compounds, and other frozen materials were more common beyond the frost line. The process of turning these microscopic particles into kilometer-sized planetesimals was one of the most delicate and improbable steps in solar system formation. For particles to stick together and grow, their collisions had to be gentle. Too much energy, and they would simply bounce apart or shatter into even smaller pieces. In the inner solar system, static electricity played a crucial role in these early stages. When tiny dust grains collided gently, weak electrostatic forces could cause them to stick together, forming fluffy aggregates that were more empty space than solid material. These aggregates could then collide with other particles, gradually growing larger and denser. But there was a major obstacle to overcome. As particles grew larger, their collisions became more energetic. Objects about the size of a pebble or a boulder were particularly vulnerable. They were too large to be held together by weak electrostatic forces, but not yet massive enough for gravity to become important. This size range, around 1 meter in diameter, became known as the meter barrier, and it nearly prevented planet formation entirely. Fortunately, the protoplanetary disk wasn't a perfectly smooth, uniform environment. Turbulence created by magnetic fields and thermal gradients led to the formation of temporary concentrations where particles could be trapped and compressed. In these high-density regions, particles could collide more frequently and with the right energies to promote sticking rather than destruction. Another important process was what scientists call streaming instabilities. As particles drifted through the disk, they interacted with the surrounding gas in complex ways that could cause them to concentrate into dense clumps. When these clumps became dense enough, gravity could take over and cause them to collapse directly into planetesimals, bypassing the problematic meter barrier entirely. The formation of the first planetesimals was remarkably rapid once it began. Within perhaps 1 to 2 million years of the Sun's formation. The inner solar system contained thousands of rocky bodies ranging from 1 to 100 kilometers across. These planetesimals were the fundamental building blocks from which all larger objects would eventually form. Each planetesimal was unique, reflecting the specific conditions where it formed. Some were rich in metallic iron, condensed from the hottest regions close to the Sun. Others were primarily composed of silicate minerals formed at moderate temperatures. Still others, forming beyond the frost line, contained significant amounts of water ice and organic compounds. The planetesimals weren't static objects. They orbited the Sun in elliptical paths that often crossed each other, leading to frequent collisions. Most of these encounters were gentle enough that the objects could merge rather than shatter, allowing planetesimals to grow into larger and larger bodies. But not all planetesimals survived this era of frequent impacts. Many were shattered by high-energy collisions, their fragments either reaccumulating into new objects or being scattered throughout the solar system. Some fragments were small enough to be blown out of the system entirely by the solar wind, while others settled into stable orbits where they remain today as asteroids and comets. The planetesimals also began to show the effects of internal heating. Radioactive elements incorporated into their structures during formation decayed and released energy. For the larger planetesimals, this heat was sufficient to melt their interiors, allowing denser materials like iron to sink toward the center, while lighter silicates floated upward. This process, called differentiation, created objects with distinct layers, metallic cores surrounded by rocky mantles. Some planetesimals experienced even more dramatic heating. If they contained significant amounts of water ice, the radioactive heating could create temporary atmospheres of water vapor. When these objects collided with each other, they could transfer water and other volatile materials, beginning the complex process of distributing these crucial materials throughout the forming solar system. The outer regions of the disk, beyond the frost line, told a different story. Here, where water ice could remain stable, planetesimals formed more rapidly and grew larger than their inner solar system counterparts. The additional solid material provided by ice meant that these outer planetesimals could reach masses of 10 to 20 Earth masses, large enough to begin capturing gas from the surrounding disk. This difference in composition and growth rate between the inner and outer regions would prove crucial for determining the final architecture of the solar system. The inner regions would produce small, rocky planets, while the outer regions would become the realm of the gas giants. As this first generation of planetesimals evolved and grew, they were setting the stage for the next phase of solar system formation, the assembly of the terrestrial planets. In the inner regions of the solar system, where temperatures remained high enough to vaporize most ices, a violent and spectacular process was beginning. The thousands of planetesimals that had formed during the previous era were embarking on a collision course that would last for tens of millions of years, and ultimately produce the 4 terrestrial planets we know today. This wasn't a gentle process of gradual accumulation. As planetesimals grew larger, their gravitational attraction became stronger, allowing them to perturb each other's orbits and cause increasingly violent collisions. What began as a relatively orderly system of objects in circular orbits gradually evolved into a chaotic swarm of planet-sized bodies following highly elliptical and inclined paths. Astronomers call this the era of oligarchic growth, because a few large objects began to dominate their neighborhoods, consuming smaller bodies and growing rapidly at the expense of their competitors. These planetary embryos, as they're known, could reach masses comparable to Mars, or even larger, before the final assembly phase began. The early Earth was one of these embryos, but it was far from alone. Computer simulations suggest that the inner solar system once contained as many as 50 to 100 such objects, each massive enough to qualify as a planet by today's standards. Most of these worlds were doomed to destruction in the violent collisions that followed. The collisions between planetary embryos were events of almost incomprehensible energy. When 2 Mars-sized objects struck each other at typical speeds of 10 to 15 kilometers per second, the energy released was sufficient to melt both bodies entirely, creating vast magma oceans that could take millions of years to cool and solidify. These impacts didn't just melt rock, they vaporized it. The early Earth and its siblings were surrounded by thick atmospheres of rock vapor, glowing clouds of silicate materials that had been blasted into space by the force of collision. These rock atmospheres could persist for thousands of years before finally cooling and condensing back onto the planetary surfaces. Each major impact also had the potential to strip away any atmosphere that had previously accumulated. The early terrestrial planets may have gained and lost dozens of atmospheres during this period, as each collision reset the process of atmospheric evolution. The heat generated by these impacts had profound effects on planetary interiors as well. The energy was sufficient to melt entire planets, allowing heavy materials like iron to sink toward the center, while lighter silicates floated upward. This process of core formation was crucial for establishing the internal structures that still characterize the terrestrial planets today. Not all planetary embryos survived to become modern planets. Many were destroyed entirely in collisions, their material scattered, and eventually reincorporated into other growing worlds. Others were ejected from the inner solar system entirely, flung into the outer solar system or beyond by gravitational encounters with their larger neighbors. Mars appears to have formed relatively quickly during this period, perhaps within just 2 to 4 million years of the beginning of planetesimal formation. Its rapid formation may have allowed it to avoid some of the most violent collisions that affected the Earth-Venus region, explaining why Mars is so much smaller than its inner neighbors. Venus and Earth, being closer to the Sun and located in a region with more raw material, took longer to assemble. The process of their formation may have continued for 50 to 100 million years, with each planet experiencing dozens of major impacts during their growth. Mercury presents a special case. Today it has an unusually large iron core relative to its size, suggesting that it experienced a particularly catastrophic collision that stripped away much of its silicate mantle. This impact may have occurred late in Mercury's formation, after it had already differentiated into a core and mantle structure. The asteroid belt, located between Mars and Jupiter, preserves evidence of this violent era. Many asteroids show signs of having been heated to high temperatures, melted, and differentiated, indicating that they were once part of much larger objects that were subsequently shattered by collisions. The asteroid belt is essentially a graveyard of failed planets, objects that began the process of terrestrial planet formation, but were disrupted before they could complete it. By the end of the terrestrial planet formation era, the inner solar system had been transformed from a crowded region containing hundreds of planetary embryos into the relatively sparse system we see today, with just 4 surviving planets and a scattered population of asteroids representing the leftover debris. But the most dramatic changes were still to come. Beyond the frost line, where ice could remain stable, an entirely different class of planets was taking shape. In the colder reaches of the protoplanetary disk, beyond the frost line where water ice could remain stable, a very different story was unfolding. Here, the additional solid material provided by frozen water, carbon dioxide, and other ices meant that planetesimals could grow much larger and faster than their counterparts in the inner solar system. The frost line, located at roughly 3 to 4 astronomical units from the Sun, represented a fundamental boundary in the early solar system. Inward from this line, temperatures were too high for water ice to remain stable, limiting the available aholid material to rocky and metallic particles. Outward from the line, ice could accumulate, roughly tripling the amount of solid material available for planet formation. This abundance of building material allowed the outer planetesimals to reach critical masses much more quickly. When a planetesimal grew to about 10 Earth masses, something remarkable happened. It became massive enough to begin capturing gas directly from the surrounding protoplanetary disk. The formation of gas giant planets required a delicate balance of timing. The solid cores had to reach sufficient mass, while there was still substantial gas remaining in the disk. Since the disk was gradually dissipating due to the solar wind and other processes, gas giant formation had to occur within the first 10 million years of solar system formation. Jupiter was the first and most successful of the gas giants. Its core, composed of rock, ice, and metals, reached the critical mass needed for gas accretion relatively quickly, perhaps within just 3 to 5 million years. Once gas accretion began, it proceeded rapidly. Jupiter's massive atmosphere was assembled in perhaps just a few 100,000 years, as gas from the surrounding disk spiraled inward and was captured by the growing planet's gravity. The process wasn't smooth or steady. As Jupiter grew, its gravitational influence began to affect the motion of gas and dust throughout the outer solar system. The planet created gaps and spirals in the disk, concentrating material in some regions while depleting it in others. These density variations affected the formation of the other planets and may have triggered the formation of Jupiter's own satellite system. Saturn formed somewhat later and under more challenging conditions. By the time Saturn's core reached the critical mass for gas accretion, the disk had already been partially depleted by Jupiter's growth and the ongoing dissipation processes. As a result, Saturn captured less gas relative to its core mass, giving it a lower overall density than Jupiter. The formation of Uranus and Neptune was even more complex. These planets may have begun forming in the region between Jupiter and Saturn, where there was more solid material available. However, gravitational interactions with the growing gas giants caused them to migrate outward to their current positions. This migration wasn't a gentle drift. Computer simulations suggest that the outer planets experienced dramatic orbital changes during the first billion years of solar system history. Jupiter may have migrated inward to within 1.5 astronomical units of the Sun before being pulled back outward by gravitational interactions with Saturn. This grand tack migration had profound effects throughout the solar system. It scattered planetesimals and embryos from the asteroid belt, prevented Mars from growing larger, and may have delivered water-rich materials to the inner planets. The migration also affected the formation and evolution of the planet's satellite systems. The gas giants didn't just capture gas during their formation. They also accumulated substantial populations of solid objects. Some of these became the planet's major satellites, while others formed the complex ring systems that we observe today around all 4 giant planets. The capture of gas by the giant planets was also responsible for creating their distinctive atmospheric compositions. While the planets' cores were composed of the same rocky and icy materials found throughout the solar system, their atmospheres were captured directly from the protoplanetary disk, and thus preserved the primordial composition of hydrogen and helium that dominated the early solar system. The rapid formation of the gas giants had cascading effects throughout the solar system. Their gravitational influence affected the orbits of smaller objects everywhere, from the asteroid belt to the outer reaches of the system. They also began the process of clearing their orbital zones, either capturing smaller objects as satellites or flinging them into different orbits. By the time the gas giants had reached their current masses, roughly 10 million years after the Sun's formation, the protoplanetary disk was beginning to dissipate. The intense solar wind and radiation pressure were gradually clearing away the remaining gas, bringing the era of rapid planet formation to a close. But the solar system was still far from the stable, orderly place we know today. The gravitational influence of the newly formed giant planets was reshaping orbits throughout the system, setting the stage for one of the most dramatic events in our cosmic history. Around 30 to 50 million years after the solar system's formation, when the inner planets had largely assembled and the gas giants had settled into more stable orbits, a catastrophic collision occurred that would forever change the Earth-Moon system. A Mars-sized object, which scientists have named Theia, was following an orbit that gradually brought it closer and closer to the early Earth. Theia had formed in roughly the same region as Earth, but gravitational perturbations from the giant planets had slowly altered its path until a collision became inevitable. The impact itself occurred at a relatively low angle and speed compared to typical planetary collisions. Rather than striking Earth head-on, Theia delivered a glancing blow that was catastrophic, yet not completely destructive. The collision released energy equivalent to billions of nuclear weapons, instantly vaporizing Theia's outer layers and blasting away a significant portion of Earth's early mantle. The impact had several profound effects on Earth. First, it tilted our planet's rotational axis to the current 23.5 degrees, giving Earth its seasons. Second, it dramatically increased Earth's rotation rate, creating a day that lasted only 5 to 6 hours. Third, it completely melted Earth's surface, creating a global magma ocean that glowed like a star. The debris from the collision didn't simply fall back to Earth or escape into space. Instead, it formed a disk of hot, vaporized rock orbiting our planet. This debris disk was incredibly dense and hot, glowing brilliantly in the infrared as rocky materials began to condense and collide with each other. Within this disk, the moon began to form through a process remarkably similar to planet formation itself. Small particles condensed from the vapor, stuck together to form larger clumps, and gradually accumulated into a single large body. The entire process was astonishingly rapid by geological standards, taking perhaps only 100 to 1,000 years. The early moon was dramatically different from the gentle companion we see today. It orbited only about 15,000 miles from Earth, close enough to appear 20 times larger in the sky than it does now. The gravitational interaction between Earth and this nearby moon created enormous tidal forces that kept both bodies partially molten for millions of years. Earth's rapid rotation and the moon's proximity combined to create tides hundreds of times stronger than anything we experience today. These tides didn't just affect the oceans, which didn't exist yet, but the molten rock itself, causing the entire planet to flex and bulge as it spun. Over millions of years, tidal friction began to slow Earth's rotation and push the moon gradually outward. This process, which continues today at a rate of about 1.5 inches per year, has been steadily lengthening our days and enlarging the moon's orbit throughout Earth's history. The moon's formation may have been crucial for the eventual development of life on Earth. The collision that created it may have stripped away Earth's original atmosphere, allowing a new one to form from volcanic outgassing. The moon's gravitational influence also helped stabilize Earth's rotational axis, preventing the dramatic climate variations that would have occurred if our planet wobbled chaotically. As the debris from the giant impact settled and the moon moved into a more distant orbit, the solar system entered a period of relative calm. But this peace would not last. Hidden in the outer reaches of the system, gravitational instabilities were building that would soon unleash another period of cosmic violence. Roughly 600 million years after the formation of the solar system, when the planets had settled into what seemed like stable orbits, the delicate gravitational balance that had maintained the peace was finally disrupted. The trigger was a resonance between Jupiter and Saturn, a point in their orbital evolution where Jupiter completed exactly 2 orbits for every one of Saturn's. This 2-to-1 resonance created powerful gravitational perturbations that rippled throughout the outer solar system. The orbits of Uranus and Neptune became unstable, causing these ice giants to migrate outward into a region populated by countless icy planetesimals left over from the era of planet formation. The migration of Neptune was particularly dramatic. As it moved outward, it encountered a vast population of small icy bodies in what would become the Kuiper Belt. Most of these objects were gravitationally scattered, some ejected from the solar system entirely, others flung inward toward the sun and the inner planets. This cosmic billiard game unleashed what astronomers call the Late Heavy Bombardment, a period of intense impacts that lasted several 100 million years. The Moon's surface still bears the scars of this era in the form of large impact basins like Mare Imbrium and Mare Orientale, circular features hundreds of miles across created by the impact of objects dozens of miles in diameter. Earth, with its larger gravitational field, experienced an even more intense bombardment. Some of the impacting objects were hundreds of miles across, large enough to excavate craters the size of entire continents and to boil away Earth's oceans temporarily. The energy released by the largest impacts was sufficient to melt portions of the planet's crust and create temporary atmospheres of rock vapor. Paradoxically, this period of destruction may also have been crucial for the development of life on Earth. Many of the impacting objects were rich in water ice and organic compounds, materials that may have been largely absent from the inner solar system after the violent era of terrestrial planet formation. The bombardment delivered these essential ingredients for life to Earth's surface. Mars and Venus experienced similar bombardments, though the effects varied depending on each planet's size and atmospheric properties. Mars, being smaller, retained less of an atmosphere to protect its surface, while Venus's thick atmosphere may have caused many impactors to break up before reaching the ground. The asteroid belt, caught between the gravitational influences of Jupiter and the migrating outer planets, was also dramatically reshaped during this period. Many of the asteroids we see today are fragments of larger objects that were shattered by collisions during the Late Heavy Bombardment. As the outer planets finally settled into their current orbits, the bombardment gradually subsided. Neptune's outward migration had cleared most of the small bodies from its path, while the remaining population settled into more stable orbits in what we now call the Kuiper Belt and Oort cloud. The Late Heavy Bombardment marked the end of the solar system's violent youth. From this point forward, impacts would be much less frequent, allowing stable surfaces to persist, and on at least one world, life to take hold and flourish. But even as the rain of asteroids and comets subsided, the planets themselves were still evolving, each developing its own unique atmospheric character. As the solar system emerged from the chaos of the Late Heavy Bombardment, each planet began to develop its own atmospheric personality. The process was gradual and complex, shaped by each world's mass, distance from the sun, magnetic field, and geological activity. Earth's early atmosphere bore little resemblance to the air we breathe today. It was composed primarily of carbon dioxide, nitrogen, water vapor, and trace amounts of other gases released by volcanic activity. There was virtually no free oxygen, a gas that would not become abundant until life itself began to transform the atmosphere billions of years later. The young Earth was a world of extremes. Volcanic activity was much more intense than today, constantly releasing gases from the planet's interior into the atmosphere. The surface was dominated by impact craters, lava flows, and the first tentative formations of solid crust as the global magma ocean finally cooled and solidified. Water vapor in the atmosphere gradually condensed as the planet cooled, creating the first oceans. But these early seas were quite different from modern oceans. They were likely hot, acidic, and rich in dissolved minerals leached from the volcanic rocks that dominated the surface. Venus, Earth's near twin in size, followed a very different atmospheric evolution. Early in its history, Venus may have had oceans and a climate not unlike Earth's. But its proximity to the sun ultimately doomed these favorable conditions. As the sun gradually grew brighter over hundreds of millions of years, Venus experienced a runaway greenhouse effect. Water vapor in Venus's atmosphere absorbed heat from the sun, warming the planet further and causing more water to evaporate. This process accelerated until the oceans boiled away entirely, leaving behind the thick, carbon dioxide-rich atmosphere we observe today, with surface temperatures hot enough to melt lead. Mars, being smaller and more distant from the sun, faced different challenges. Early Mars likely had a thicker atmosphere and a warmer climate, possibly warm enough for liquid water to flow on its surface. Evidence for this warmer period is preserved in the geological record. Ancient river valleys, lake beds, and mineral deposits that could only have formed in the presence of liquid water. But Mars's smaller size meant it had less gravitational pull to retain its atmosphere, and its weaker magnetic field provided less protection against the solar wind. Over billions of years, much of Mars's atmosphere was gradually stripped away, leaving behind the thin, cold environment we see today. The gas giants retained their original atmospheres almost unchanged since their formation. These dense envelopes of hydrogen and helium, captured directly from the protoplanetary disk, have been stirred and heated by the planet's internal energy sources, but remain fundamentally similar to the composition of the early solar system. Jupiter's atmosphere is particularly dynamic, driven by the planet's rapid rotation and internal heat source. The beautiful bands and storms we observe, including the Great Red Spot, are manifestations of this atmospheric circulation, patterns that have persisted for centuries and may continue for millennia more. Saturn's atmosphere, while similar in composition to Jupiter's, shows different behavior due to Saturn's lower mass and density. The planet's spectacular ring system also interacts with its atmosphere, creating spokes and other features that scientists are still working to understand. Uranus and Neptune, the ice giants, have atmospheres that reflect their different formation histories. These planets contain much higher proportions of water, methane, and ammonia relative to hydrogen and helium, giving them distinctly different properties and colors compared to Jupiter and Saturn. The atmospheric evolution of the planets was also influenced by their satellite systems. Large moons could provide additional sources of gas through volcanic outgassing or impact vaporization. They could also gravitationally stir their parent planet's atmosphere, affecting circulation patterns and weather systems. Some moons developed atmospheres of their own. Titan, Saturn's largest moon, has a thick nitrogen atmosphere with methane clouds and hydrocarbon rain, creating a complex weather system that rivals Earth's in its sophistication. Other moons, like Jupiter's Io, have thin atmospheres created by ongoing volcanic activity. As the atmospheres of the planets evolved, they also began to interact with the solar wind and radiation from space in complex ways. Planets with strong magnetic fields, like Earth and Jupiter, could trap charged particles and create radiation belts and auroras. Planets without such protection gradually lost their atmospheres to space. The development of planetary atmospheres was not a one-time event, but an ongoing process that continues today. Volcanic activity, impacts, atmospheric escape, and biological processes all continue to modify planetary atmospheres over geological timescales. On Earth, the emergence of life would eventually transform the atmosphere completely, replacing a carbon dioxide-rich environment with the oxygen-rich air that characterizes our world today. This transformation would take billions of years and would itself make possible the incredible diversity of life that now inhabits our planet. Throughout this atmospheric evolution, countless small bodies continued to orbit the Sun, remnants of the solar system's formation that preserved crucial information about its early history. While the planets were developing their unique atmospheric characters, the solar system was also populated by a vast array of smaller objects, the remnants and survivors of the formation process. These asteroids, comets, and other small bodies would become crucial for understanding the solar system's history and would continue to play important roles in its ongoing evolution. The asteroid belt, located between Mars and Jupiter, contains hundreds of thousands of objects ranging in size from tiny pebbles to dwarf planets hundreds of miles across. These bodies are the leftover planetesimals that never managed to accumulate into a full-sized planet, prevented from doing so by Jupiter's powerful gravitational influence. The asteroids tell a story of violence and disruption. Many show evidence of having been heated to high temperatures early in their history, indicating they were once part of much larger, differentiated objects that possessed metallic cores and rocky mantles. These parent bodies were subsequently shattered by collisions, leaving behind fragments that preserve samples of planetary interiors. Some asteroids are rich in metals, particularly iron and nickel, and represent the cores of these disrupted parent bodies. Others are composed primarily of rocky materials from the mantles, while still others preserve primitive materials that date back to the very beginning of solar system formation. The distribution of asteroid types provides clues about the temperature structure of the early solar system. Closer to the Sun, we find asteroids rich in refractory materials that could survive high temperatures. Further out, beyond the former position of the frost line, we find asteroids that contain water-bearing minerals and organic compounds. Beyond Neptune's orbit lies the Kuiper Belt, a region of icy bodies that represents the outer solar system's equivalent of the asteroid belt. These objects, formed in the cold outer reaches of the protoplanetary disk, and are composed primarily of various ices mixed with rocky materials. The Kuiper Belt objects include some of the most pristine materials in the solar system. Unlike the asteroids, which have been heated and altered by billions of years of evolution, many Kuiper Belt objects have remained virtually unchanged since their formation. They preserve samples of the original ices and organic compounds that were present in the outer regions of the protoplanetary disk. Pluto, now classified as a dwarf planet, is one of the largest known Kuiper Belt objects. Its complex system of moons and its unusual orbital characteristics provide insights into the dynamical evolution of the outer solar system during the late heavy bombardment. Even more distant is the Oort cloud, a spherical shell of cometary objects that may extend halfway to the nearest star. These objects are so far from the Sun that they are barely bound by its gravity, and their orbits can be easily perturbed by passing stars or galactic tidal forces. Comets are among the most spectacular reminders of the solar system's formation. When their highly elliptical orbits bring them close to the Sun, the heat vaporizes their ices, creating the beautiful tails of gas and dust that have inspired humans throughout history. These tails carry away materials from the comet's surface, providing scientists with samples of primitive solar system materials. The study of comets has revealed that they contain not just water ice, but also frozen carbon dioxide, methane, ammonia, and complex organic molecules. Some comets have been found to contain amino acids and other biological precursors, suggesting that impacts by comets during the late heavy bombardment may have delivered some of the raw materials necessary for life to Earth. The small bodies of the solar system also preserve evidence of the isotopic compositions that characterized different regions of the protoplanetary disk. By studying meteorites, which are fragments of asteroids that have fallen to Earth, scientists can reconstruct the temperature and chemical conditions that existed during the earliest phases of solar system formation. Some meteorites contain tiny grains of material that actually predate the solar system's formation. These pre-solar grains condensed in the atmospheres of dying stars and were incorporated into the molecular cloud from which our solar system formed. They provide direct samples of stellar nucleosynthesis and insights into the galactic chemical evolution that preceded our sun's birth. The small bodies continue to evolve today through ongoing collisions, sublimation, and gravitational interactions. New asteroids are discovered regularly, and occasionally one is found on a trajectory that will bring it close to Earth, reminding us that the solar system remains a dynamic and sometimes dangerous place. As we follow the story of these small bodies, we also begin to see how the solar system's architecture was shaped by a process that continues today: the slow gravitational dance that moves planets and small bodies into new configurations over cosmic time. As the solar system settled into its mature configuration, the planets didn't simply remain frozen in their formation positions. Instead, they continued to migrate slowly through a complex gravitational dance that reshaped the entire system over hundreds of millions of years. This migration was driven by gravitational interactions between the planets themselves and with the remaining population of small bodies. When a planet gravitationally scattered a smaller object, conservation of momentum required that the planet's own orbit change slightly in response. Individually, these changes were minuscule, but over millions of years, they could add up to significant orbital evolution. Jupiter, being the most massive planet, had the greatest influence on this process. Early in its history, Jupiter may have migrated significantly inward, approaching to within 1.5 astronomical units of the Sun before being pulled back outward by gravitational interactions with Saturn. This inward then outward migration, called the Grand Tack model, could explain several puzzling features of the inner solar system. The Grand Tack may explain why Mars is so much smaller than Earth and Venus. If Jupiter migrated inward during Mars's formation, it would have gravitationally scattered much of the material that Mars might otherwise have accreted, stunting the planet's growth and leaving it with only about 10% of Earth's mass. Saturn's orbital evolution was closely linked to Jupiter's, but the interaction was complex and dependent on the precise timing of their formation and early migration. Computer simulations suggest that Saturn's influence was crucial for reversing Jupiter's inward migration and establishing the current orbital architecture of the giant planets. The migration of the outer planets had dramatic effects throughout the solar system. As Neptune moved outward, it encountered the primordial Kuiper Belt, a region that was originally much more densely populated than it is today. Neptune's gravity scattered most of these objects, some into the inner solar system, where they contributed to the late heavy bombardment, others completely out of the solar system. This scattering process left behind the current Kuiper Belt, which contains only a few percent of its original mass. The objects that remain are arranged in complex orbital patterns that reflect their interactions with Neptune over billions of years. Some are trapped in resonances with Neptune, completing exact integer ratios of orbits, while others follow highly inclined or elliptical paths. Uranus underwent particularly dramatic changes during this period of migration. Its extreme axial tilt, which causes it to essentially roll along its orbital path rather than spinning upright like other planets, may be the result of a massive collision that occurred during the era of planetary migration. Such a collision could have been triggered by orbital instabilities that brought large objects from the outer solar system into the region of the ice giants. The migration process was not smooth or steady. Instead, it likely proceeded in fits and starts, with periods of rapid change separated by intervals of relative stability. Resonance crossings, where the orbital periods of two planets achieved simple integer ratios, could trigger sudden instabilities that dramatically altered the orbits of multiple planets. These orbital changes also affected the satellites of the giant planets. Some moons may have been captured during close encounters with migrating planets, while others may have been lost to space. The complex satellite systems we observe today around Jupiter, Saturn, Uranus, and Neptune represent the survivors of this tumultuous period. Even the asteroid belt bears the scars of planetary migration. The current distribution of asteroids, with significant gaps at certain distances from the Sun, reflects the gravitational influence of Jupiter as it moved through different orbital configurations. Objects trapped in resonances with Jupiter were systematically removed from the belt, creating the gap structure we observe today. The migration process gradually slowed as the solar system evolved, and the population of small bodies that could facilitate further orbital changes was depleted. Today, the planets continue to migrate, but at much slower rates. Tidal interactions with the Sun and with their satellites cause gradual orbital evolution that will continue for billions of years into the future. Understanding planetary migration has revolutionized our knowledge of solar system formation and has important implications for the study of exoplanetary systems. Many of the planetary systems discovered around other stars show evidence of extreme migration, with giant planets orbiting very close to their host stars. Our solar system's more moderate migration history may be one reason why it was able to maintain stable conditions suitable for the development of life. As the grand migration era came to an end, the solar system finally began to resemble the orderly, stable system we inhabit today. The planets had found their long-term homes. The small body populations had been sculpted into their current distributions, and the stage was set for the long, slow evolution that continues to this day. And so, after nearly 5 billion years of cosmic construction, our solar system had transformed from a simple cloud of gas and dust into the complex, beautiful family of worlds we call home today. The violent birth pangs were over, the dramatic migrations had ended, and the system had settled into the stable configuration that has persisted for billions of years. The Sun, now middle-aged and burning steadily, provides the reliable energy that has allowed life to flourish on at least one world. Its nuclear furnace converts millions of tons of hydrogen into helium every second, releasing the light and warmth that makes our planet habitable. This stellar hearth has burned without interruption for 4.6 billion years and will continue for another 5 billion years before beginning its transformation into a red giant. Earth has found its perfect balance in the habitable zone, that narrow region around the Sun where liquid water can exist on a planet's surface. Not too hot, like Venus, not too cold, like Mars, but just right for the complex chemistry of life to unfold. The Moon continues its slow drift away from Earth, gradually lengthening our days and stabilizing our planet's climate through its gravitational influence. Mars stands as a reminder of how different planetary evolution can be. Its ancient river valleys and lake beds tell the story of a world that once had flowing water and perhaps a thicker atmosphere. Though cold and dry today, Mars preserves in its rocks and polar ice caps a record of the solar system's early history and the possibilities for life beyond Earth. The gas giants continue their stately orbits, serving as gravitational shepherds that protect the inner solar system from the worst of the remaining cometary bombardment. Jupiter, in particular, acts as a cosmic vacuum cleaner, using its immense gravity to capture or deflect potentially dangerous objects before they can threaten the inner planets. The asteroid belt, that graveyard of a planet that never was, provides a constant reminder of the violent processes that shaped our system. Yet these rocky remnants also preserve pristine samples of the materials from which the planets formed, allowing scientists to study solar system formation by examining meteorites that fall to Earth. Beyond Neptune, the Kuiper Belt and Oort cloud continue their patient vigil, storing billions of icy bodies that occasionally venture inward as comets, bringing with them water and organic compounds that may have been crucial for the origin of life on Earth. The story of solar system formation is far from over. Even today, new small bodies are being discovered regularly. Asteroid and comet impacts continue to occur, though at a much reduced rate compared to the violent early eons. The planets continue their slow gravitational dance, gradually modifying their orbits through tidal interactions. Looking ahead, the solar system will continue to evolve over cosmic timescales. In about 1 billion years, the gradually brightening sun will make Earth too hot for liquid water. In 5 billion years, the sun will begin its transformation into a red giant, potentially engulfing the inner planets. But these changes are so far in the future that they are essentially unimaginable from a human perspective. For now, our solar system represents a perfect balance between the forces of creation and destruction, order, and chaos that have shaped it over billions of years. It is a place where rocky worlds orbit close to their star, where giant planets sweep through the outer darkness, where countless small bodies preserve the memory of cosmic genesis, and where, on at least one world, matter has organized itself into life and consciousness. The elements that make up your body were forged in the nuclear furnaces of ancient stars and scattered into space by stellar explosions. They drifted for millions of years in the cold darkness of the molecular cloud before being gathered together in the swirling disk that surrounded our young sun. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was present in that primordial disk 4.6 billion years ago. You are, quite literally, made of solar system materials, assembled from the same karmic dust that formed the planets and moons, the asteroids and comets. Your existence is intimately connected to the story of solar system formation, to the patient work of gravity and chemistry and physics that transformed a simple cloud into the complex, beautiful system we inhabit. And in your ability to contemplate this cosmic story, to trace the connections between your own existence and the formation of worlds, the universe has found a way to know itself. Through human consciousness, the solar system has developed the capacity to understand its own origins, to appreciate its own beauty, and to wonder about its place in the larger cosmos. As you rest tonight, carried by a planet that spins peacefully through space, remember that you are part of this ancient story. You are riding on a world that condensed from cosmic dust, orbiting a star that ignited in the heart of a collapsing cloud, in a solar system that represents one of the universe's most successful experiments in creating complexity from simplicity. The gentle gravity that holds you in place is the same force that gathered the first planetesimals, that assembled the planets, that continues to guide the orbital dance of worlds. The elements in your body have traveled across space and time to be here, now, in this moment of cosmic history. Sleep peacefully, knowing that you are home in a solar system that spent billions of years preparing for your arrival. Dream of the vast scales of space and time that brought you into being, of the patient work of cosmic forces that created a place where life could emerge and flourish. In the quiet darkness of space, our solar system continues its ancient journey around the galaxy, a small but precious island of order in the cosmic sea, carrying with it the precious cargo of life and consciousness that emerged from its billion-year construction project. Good night.